Let's see. All right, so looking at notes 2-1, notes for Friday. So it's a page and a half of notes, but it goes fairly quickly because most of it's already filled in. So first off is a relation, and specifically a relation versus a function, and how are they similar, how are they different. A relation is any set of ordered pairs. And it doesn't even have to be it's a set of ordered pairs, but it's not necessarily a list of ordered pairs. It could also be an equation. So it could be a list of x comma y's, but it could also be an equation. Like a simple one would be x squared plus y squared equals 1.
Good afternoon, Mustang. Teachers.
Or y equals 7x plus 3. Like those are equations or a list of ordered pairs. Any set of points, however they're defined, is a relation, as opposed to a function, which we'll get to in a minute. Domain and range we talked about on Thursday. Domain's the x's, range is the y's. We'll kind of cruise through that. Relations can be described by, here's what I was saying a minute ago, you can either see it on a graph, you can see it as an equation, it could just be a list of ordered pairs. Mapping diagram, I don't know if you recognize that term, but that's a mapping diagram down there at the bottom right. It maps the domain onto the range, or the x onto the y. You've seen tables for a long time. A written rule would be like a word problem kind of thing, where it would describe how the x's and y's are related. Okay, so a relation is any number of those things that ties together an x and a y. A function is a type of relation. In fact, we could almost draw a kind of a Venn diagram here. You got relations, and then as a subset of relations, you have functions. It's one of those all functions are relations, but not all relations are functions thing. Squares and rectangles, right? All squares are rectangles, but not all rectangles are squares. A function is a special type of relation. And you've probably seen this picture before in Algebra 1. I'll draw the picture in a minute. There's only one output for each input. For every x, there's only one y. I don't get this every girl there's a guy thing, because that gets into which way we're x's and y's. I don't know. Throw that one out. Let's do a picture of a function, and a picture with a mapping diagram. That's the fancy term. I like to think of functions as vending machines. So if I push button 1, I get drink A. If I push button 2, I get drink B. And if I push button 3, I also get drink B. So the question for you is that a function?
Yes.
Uh-oh, I heard yeses and nos.
Yes.
Yes, it's a yes. If you push the button, you know what you're going to get. You get exactly one thing, right? You can almost tell it's a function just by looking at the left-hand side. Each button goes to one thing. It doesn't really matter what it goes to. Each button has a defined output. Each input goes to one output. So yes, this is a function. If you think of the vending machine, if you push button 1, you get a Coke. You push button 2, you get a Dr. Pepper. Push button 3, you also get a Dr. Pepper, but that's fine. That's a functioning vending machine. What would a not functioning vending machine look like? How could I draw one of those? Yes. So he said 3 goes to B and A. So 1 goes to A. 2 goes to B, and 3 goes to B and A. So that's not a functioning vending machine, right? If you hit button 3 and you get a Coke and a Dr. Pepper, like that's a win for you. Congrats. But that's not a functioning vending machine. Or maybe you don't get both, maybe you get one or the other, but then you don't know which one you're getting. That's not good. So this is not a functioning vending machine. So if you know what you're going to get, if one input leads to one output, you got a functioning vending machine. You have a function. Now there's a special type of function. where things are matched up exactly, like 1 goes to A, oops, that needs to be a 2 goes to B, and 3 goes to C. Get my face out of the way here. That has a special name. That is a one-to-one function. You can almost think of it as a reversible function, a backwards function. You can go backwards. One way to think of backwards is if there's somebody standing next to the vending machine with a drink in their hand, if you can tell what button they pushed, it's a one-to-one function. They map up exactly. If someone is standing next to this vending machine with a drink B in their hand, you don't know which button they pushed. Maybe they pushed 2, maybe they pushed 3, but it wasn't one-to-one, so you can't tell where that drink came from or what button that came from. If you're standing next to this vending machine and somebody's holding drink C, you know they pushed 3 because it's a one-to-one mapping. So both functions, but this is a special type of function. It also means its inverse is a function. That's the backwards part of it. All right, so let's see if we can make sense of all that with some point examples here. So this first set of points, you tell me, is that a function? No, why not? Yeah, we got a problem with 6 here. 6 goes to 4 and 6 goes to 1. So it's like if you push the 6 button, you don't know if you're getting a 1 or a 4. So that's not a function. And if it's not a function, then the one-to-one is a subset of a function. So if it's not a function, one-to-one, the question doesn't even make sense. For the domain, you know that's the x values. A lot of times to look fancy, we'll put it in the kind of fancy brackets there and then list the x values. I'm going to put them in order, but you don't have to put them in order. And the brackets help us differentiate, because if I put it in parentheses, it would look like the ordered pair 1, 6. But I don't want it to be the ordered pair 1, 6. I want it to be the list of x's 1 and 6. It would also be okay if you put 6 and 1, like the order they appear. So sometimes I put them in numerical order, other times I put them in the order they appear. It doesn't matter. It's just a list. Range would be the y values. So instead of thinking about putting them in order, I'll just list them off here. 4, -5, 1. Again, it's just different ways to organize the information as to what order you put them in. If your brain wants to see them in order, then put them in order. If your brain thinks it makes more sense to just list them in the order they appear, then list them in the order they appear. Either one is okay. I would like you to use the brackets. Again, if there's 3 values, it's not really that big a deal. But when there's only 2 values, if you use parentheses, then it looks like an ordered pair. And I mean, if it's clearly labeled, it's fine. But I would rather use the bracket just so you don't get confused, and I don't get confused. We'll know what we're talking about. All right, how about this second example? Is that a function? Yeah. It is a function. All the x's go to a y. There's not one x that goes to multiple y's. Is it a one-to-one function? No, why not?
2 4s.
2 4s. So it's a function, but again, if someone's standing next to that function holding a y output of a 4, you don't know if that came from a 3 or a 2. It's not one-to-one. Domain and range, this is kind of easy at this point. We're just listing the x's, and they're already in order. 1, 2, 3. List the y's. You don't have to list them repeatedly. Like, you don't want to put 2, 4, 4. Just put 2 and 4. All right, how about this third example? Is that a function?
Yes.
There's more. Oh, yes it is. I almost got thrown off there. If you only look at the x values, you think, no, it's not a function, there's 2 1s. But then you look a little more carefully, and that's just the same point. That's kind of tricky. So yes, it is a function. Why they listed 1 point twice, I don't know. but it's a function. Is it one-to-one?
No.
No, because of those zeros. And let's don't worry about domain and range. We're perfectly competent at listing x's and y's. How about the fourth example? Is that a function?
Yes.
Yes. And is it one-to-one?
Yes.
Yeah, they all go to separate things. So it's backwardsable. That's the official math term there. If someone's standing there with a 5 as an output, you know it had to come from a 2. It's the only way they would have gotten a 5. So it's reversible. Vertical line test helps you determine whether a graph is a function or not. I think you've seen the vertical line test in Algebra 1? Yes? Okay. Super easy to use. If you can draw a vertical line and it hits twice, then that's not a function. And it's related to that repeated xy thing, because if this is my x value, then I've got two different y values, so that doesn't work as a function. What's not on here, that I think I want to add right here, is the horizontal line test. Have y'all done the horizontal line test before? Okay. So the vertical line test tells you it's a function. The vertical line test determines, you want to guess what it determines? If it's one-to-one. So if it passes the vertical and the horizontal line test, it's a one-to-one function. I guess we should be careful, because you only use the horizontal line test if you've also passed the vertical line test. But if it passes the horizontal line test, then it's one-to-one. An example, here's an easy example, like just a parabola. So is that a function?
Yes.
It is a function. Passes the vertical line test.
Doesn't pass the horizontal.
So
It's not one-to-one.
it is a function, but it's not one-to-one. So your good old vertical line test still works, but the next question that we've added this year is, well, is it a one-to-one function? Is it this special kind of function? And the horizontal line test can tell you that. And again, it's just as easy as the vertical line test. You just 90 degrees and then look for two intersections. All right, some practice. You can hardly read this. Let's mark out that first one. I don't even know what we're supposed to see on that one. On the second one, let's just answer, is it a function and is it one-to-one? Function and one-to-one. And of course, if it's not a function, the one-to-one question doesn't even matter. So is this a function? Yeah, in fact, you can tell it's a function, again, just looking at the left-hand side. It doesn't really matter where the arrows go. There's one arrow coming from each x value, so it's a function. Now, is it a one-to-one function?
No.
No. Why not?
Because 6 goes to 1 and negative 1.
Yeah, because 6 is paired with negative 1 and 1. Again, think about the vending machine. Someone's standing there next to the vending machine holding their 6 drink. You don't know what button they push to get it, so you can't go backwards, so it's not one-to-one. All right, the next page, that's just a group of words that kind of, I don't want to say mean the same thing, that always go together. The independent variable is the x variable. If it's an if-then statement, the if part is the x, the then is the y. Cause and effect kind of goes the same as if and then. You already know domain and range. So that's just a reminder of terms, and terms that are, this is grouped together. Usually, think of this as the x stuff, and that's the y stuff. So you've seen those before, you've heard all those words before, but just kind of organizing how they work together. All right, discrete versus continuous. Discrete data is a set of individual points. Points being the key word there. A continuous function is graphed with a line or a smooth curve. So a quick example, thinking about parabolas, since that's an easy one that we kind of know of. That sort of looks like a parabola. It's like the points from a parabola. That's discrete information or discrete data because it's just a set of points. If we had those same points, but then we connected a line through them, then that's not just the points, that's all those points on the line, which is like an infinite number of points. That's continuous. And this is a side note of what annoys some math teachers, because some publications don't understand math very well. Here's an example. Like if we did cars sold for 2020, 2021, 2022, and 2023. And who knows, this is millions of cars. So 2021, we're coming off of COVID, we go down a little bit, and then we recover, and then it's, I don't know, I'm just making up stuff. Is that discrete or continuous? That's discrete. It makes no sense to say how many cars did we sell in between 2020 and 2021. That doesn't even make sense. So that is definitely discrete data. What makes it look funny is when people who don't know what they're doing play connect the dots with that. And I hesitate to even do it. I'll do it with a pencil and then I'll erase it. So don't write this down. You'll see graphs like that. And that suggests that there is data in between there, but no, there can't be data if we're talking about years. So don't connect the dots if your data is discrete. That's one way to say that. But you will see that in newspapers and magazines, and they don't really know what they're doing. They just plot a graph and then they connect the dots. You're like, wait a minute, you probably should not connect those dots because that doesn't make sense. Alright, this is all fudged up down there. Let's see, what do we want to say about those? It says graph it. Let's just graph it as a reminder of what's going on here. It's an algebra review. What shape is this? It's a line. Someone almost gave the next answer. Slope-intercept form. If you were going to graph that, what would you use first?
The y-intercept.
Good, the y-intercept, the -3. Right, we begin with the b. So b is -3. I'm going to change the slope from 0.5 to 1/2 because that's a little easier to graph with, to go up 1 over 2, up 1 over 2. So there's our 1/2 x plus or minus 3. Graphing a line. How about 18? What shape is that?
Parabola.
So the x squared means it's a parabola. What about this stuff in front? What's that doing to the graph?
It's negative, so it points down.
Okay, so it points down. Yes. Do you know what the 5 does to the graph?
How wide is it?
It does. It affects how wide it is. And the bigger that number, the less wide it is, which maybe sounds backwards. It's how stretched out it is, maybe a better way to say that. So the 5 stretches it out. So we're not going to get an official sketch of this. We'll just roughly sketch a steep downward parabola. Circle the x squared is the parabola part. The negative is the down part, and the 5 is the stretch part.
Right, so the bigger the number, the thinner it is, right?
The bigger the number, the narrower it
Okay,
is.
so the steeper the slope.
Yeah, so it's kind of a, you don't want to use the word slope because that's not what it means, it's on a line, but it's kind of that same idea of how steep is it. a function notation. The x is the input. I think you know this. That's what goes in on the other side if we're going to find f of 3. I guess we should do one. F of 3 then means plug in 3. So in goes 3. So 6 minus 4 is 2. Function notation. That should be old news. Yeah, sorry. Right, whatever's in parentheses goes in for x on the other side. Now, because we just did one of those, let's skip 28 and 30. That's pretty simple. But let's do this last example. But I'm going to rewrite what h of x is, or what I think that says, because I'm not sure. But I think that's negative 4x squared minus 2x plus 5. So h of negative 2n, maybe this seems weird because we usually plug in numbers rather than letters, but it's the same process. Wherever there's an x, I'm going to put negative 2n. I'm going to replace the x with negative 2n. I'm going to replace the x with negative 2n. And everything else stays the same. Right? Because whatever's in parentheses becomes the input to that function. People still writing, so I need to slow down. I don't want to do the thing where I go so fast all you can do is copy down things without thinking about it, because then you didn't learn anything. All you did was write down what I wrote down. All right, so now we've got some cleanup work to do, but we've done the main thing. We've plugged in negative 2n wherever there was an x. So let's see here. If I square negative 2n, I've got to square the negative 2 and square the n. I guess that would be the trickiest part. Negative 2 times negative 2n would be 4n. And so negative 16n squared plus 4n plus 5. Whatever's in parentheses gets plugged in on the other side. Next thing is just more practice of the same thing, so we'll skip that. You can see what it is. It's really similar. We'd plug in 4a into x and then simplify, but let's leave that one alone. The graph, this is supposed to be easy, but some students, including my calculus students, mess this up, I think because they don't understand what's being asked. So here's a picture of f of x. And if we want f of 1, okay, I don't have an equation to plug into, but I do have a graph that tells me when x is 1, what is y equal to?
1.
1, because I'm just looking at that point right there. So f of 1 is 1. Because the inside the parentheses stuff is the x. F of 1 is the y. So I'm just using my picture to look at the x and then get the y. So once you figure out how to do these, it's super easy. But until you figure it out, obviously you'd be lost. How about f of 0? F of 0, yeah, I'd say. I mean, I guess you could argue it's negative 1.7 or 1.8, but we'll assume it's a integer. We'll say negative 2. How about f of negative 2? Well, I see what you're looking at for 0, but look up there. It looks like there's a dot there, I think, trying to tell me that f of negative 2 is 4. Right? I mean, because when x is negative 2, right, when x is like negative 1.9, the y value is 0. But when we get over to x equals negative 2, the dot is all the way up there at 4. And they put a dot there so that we'd see that.
But what about just be greater than or less than? Because the other dot isn't filled in.
Okay, the other dot's not filled in, but I don't care about we worry about that in a minute. But right now, I just want to know when x is negative 2, what's y equal to? Y equals to 4.
That's for sure.
And don't worry, we're only looking at that super narrow little slice where x is negative 2. Nowhere else matters. Now, you're right that the other end is not filled in. So what is f of 2? It's a trick question. I'll give you that as a hint.
5. 6 is less than.
It's not 5. It's not 6.
X is less than.
5.5.
Not 5.5. I told you it's a trick question.
It doesn't exist.
It doesn't exist. So you could say undefined, or you could say doesn't exist. Which a lot of times in math we'll abbreviate DNE. So if you want to use your abbreviation, you can say DNE. It doesn't exist. There's not there. Ava, what's up?
I don't know.
Sure?
Yeah, well, it's only undefined when the circle is not closed.
Correct. Yeah, when the circle's closed, there's a dot there. When the circle's open, we get close to there, but there's nothing at x equals 2.
So if that circle was closed, then it would be 5.
Yes. Yes, if the circle was closed, it would be 5. The y value would be 5. How about f of negative 3?
D&E.
Also DNE, there's nothing over there. All right, is 4 in the range of f of x? Is 4 in the range? Yeah, another way to say that is for a y value of f of x. Yes. All right, here's my y equals 4 line. And we hit the graph. We hit it 2 places even. So, yes. How about is 4 in the domain? Yeah, there's x equals 4. We don't ever get there. So, no on that one. Okay, the next 2 things I feel like are backwards, because how are you supposed to find the domain if you don't know the domain restrictions? So let's talk about the domain restrictions first. There's only 2 restrictions for now. This is one of those things where it's too much to teach all of it, and so sometimes we teach it as, oh, there's only 2, and then later on you learn that there's more, and you're like, well, wait a minute, my Algebra 2 teacher said there's only 2. No, I'm saying there's only 2 for now. Later in life there's more, but for now we only have to worry about 2. And the first issue is fractions. Like if we look at that guy, f of x equals 1 over x plus 6, there's an x value, right? Domain is x values. There's an x value that doesn't work for that equation. Like you cannot use a certain x value. Do you know what x value would make that not work? Why wouldn't negative 6 work? You're right. But put the 0 in the bottom. So for fractions, denominators can't be 0. You can't divide by 0. So that means this domain, if we write it simply, would just be x can't be negative 6, because that would make the thing blow up, not work. Now, we can get fancy and write that as an interval notation. So it's like everything except negative 6. That's what the picture would look like. So negative infinity up to negative 6, but don't include negative 6. and then start again at negative 6 without including negative 6 and going to infinity. Those say the same thing. One of them says it the fancy way with an interval. One of them says it like the more intuitive way, like, hey, x can't be negative 6. You need to know both, because if I don't ask for a certain way to write it, then I would go with the easy way, right? Just x can't be negative 6. But sometimes we'll ask for interval notation, so make sure you understand how to do that. All right, the second issue is square roots. All right, fractions you couldn't divide by 0. Square roots, what can you not take a square root of? What type of number can you not take a square root of? Okay, that's a good answer, a non-perfect square. So if I try to take the square root of 10, I don't get a nice number. But it does have a square root, right? It's 3 point something. So I could take a square root. But there's a type of number that you can't even do that with. A negative number. So square roots can't be negative. So that means we're going to take whatever's under the square root and say, how could I mathematically say not negative? What kind of equation or inequality would I write that would mean x minus 4 can't be negative? Use less than or greater than. X minus 4 has to be greater than. What does it have to be greater than? 0. Now let's be careful here. Can it equal 0? Can you take the square root of 0? Is there a number multiplied by itself that gives you 0? 0. So it can equal 0, because the square root of 0 is 0. So it can be 0, it can be positive, it just can't be negative. So we add the 4 to the other side. X has to be greater than 4. And that would be the inequality way to write that. And again, the interval way to write that. Let's see, so greater than 4, that means starting at 4 and going to infinity. We can't include infinity, but we do want to include the 4. Infinity, bracket on the 4 to include it, parentheses on infinity because we never include infinity. You can't get there.
That's the domain.
And that's the domain. So that's two different ways to write the domain. You can write it as an inequality, you can write it as an interval. And if I don't specify which way, then it doesn't matter which way you write it. If we do specify, we usually specify it as an interval because that's the fancier way to go. So let's look at these last two examples here. Working our way backwards here. So that's a fraction. What can't x be? What would be a problem there? What would make that 0? Negative 4. So some people would just look at it and just sort of figure it out. Other people would take a little bit longer way around and say, all right, let's set it equal to 0. And hopefully you don't write out all these steps, but write them if you need to. Yeah, x can't be negative 4. That's the domain. I would say be careful if you write it out this way. Sometimes students, they get so focused on setting it equal to 0 and solving it that they get x equals negative 4 and box that. And that's sort of the opposite of the right answer, right? It's like everything except negative 4. So just be careful. Make sure you're paying attention as you work these problems. Yes, ma'am.
So when answering the question, do you just put what it can't be?
For a denominator, you just put what it can't be.
Okay.
All right, this last one, it doesn't have a fraction, it doesn't have a square root. So the domain, it doesn't have any restrictions. No restrictions. Yay, that's fun. So what does that mean? What values of x are we allowed to use? Yeah, all of them. So you can use that fancy R that means all real numbers. You seen that before?
No.
It's like an uppercase R with an extra thing on it, extra stem. Or you could be fancy and use the interval notation. Because there aren't any restrictions. You can plug in anything you like. Okay, now you're ready to finish this worksheet. Is it 2 pages front and back, or a page and a half? Nope, it's 2 pages. Most of it's pretty simple, though. Like, there's even some. I hate using the word PEMDAS because I don't like phrasing it that way. Add and subtract have the same order, not different orders. So it's some pretty easy stuff. It's a review. Now, when is it due? It's going to be due on test day, but you should do it before test day. That way on Monday, you can ask questions about it. So it's assigned now. I expect it to be completed by Monday, but I'm not going to take it up until we have our test day. So this sort of puts it on you to be responsible, to work through it, to check Schoology and see let's see what I've got here. Oh, there's my emails. Whoops, that's calculus. I did want to take this time to show you. Unit 1. Again, it's a little misleading. Like Unit 1 materials is just one link, and you click it, and it blows up to include all this different stuff. Let's see, today's the 9th, so we could click on the 9th. And even though there's only one day of stuff, there's the notes. There's the notes filled in. You don't need that. There's 2 videos, one or both from Miss Craig, but you don't need that either because you were here. There's the review worksheet, and there's the review worksheet with answers. So there's tons of resources out there every day. I don't expect you to use most of them every day, but once in a while, or what I suspect you would use most of the time is the answers, right? So you're working through at home, you pull out your phone or your computer, and then you start checking and see, how am I doing? How am I doing? Am I getting them right? And sometimes we show work, sometimes we don't, just depends. And that way, come Monday, you can come in and be like, oh man, I did not understand where the 4/3 came from. How did you get that? And so this way, you can check your work and either A, feel good about it, that would be the preferred way to go, but even if you get stuck somewhere, it helps you know sort of what questions to ask the next day. And if you're absent, well, then you got all this extra stuff that you could sort through to get caught up. Let's see, here we go. Oh, that's a long video. Goodness.